Welcome. Today we will study about set theory. Right. So what is a set? A set is basically a well-defined collection of objects. So you have some objects or some elements that are well defined. So you group them together and you call that a set. Right. So let's see via some example what actually is a set in practical sense. Right. So let us take all the natural numbers from 1 to 5. So they are basically 1, 2, 3, 4 and 5. So these numbers are well defined. The term well defined means that whenever you ask anyone who has basic knowledge about mathematics, all of them will agree at once that these are all the natural numbers from 1 to 5, right? So this statement or this fact is universally true. In set theory, we accept something as well defined if that is universally true. Like, so for example, if we say that we collect a collection of good singers in India, right? So that actually does not form a set because the term good is vague in mathematical sense, right? So what can be good for one may not be good for the other, right? So in this way, we actually like distinguish what is well defined and what is not well defined, and consequently we put something in a set or it doesn't put something in a set, right? So for example, this the natural number still 100, so this is a set, right? So the planets in our solar system, that is a set, right? So number of student passing class 12 from West Bengal in 2022, that is also a set, right? So what are some non-sets? Like when generally you use an adjective to define something and that adjective is vague in mathematical sense. So suppose good batsman of India, right? So that may depend which batsman is good in terms of what, right? So some may be a good test player, some may be a good T20 player, right? So why is this set theory important? So as you know, if you organize something in a proper way, that gives you an ample space to study each of these groups individually and get properties or insight into that group that help you to develop the study of such objects, right? So set theory basically does that. So it groups like the like quantities or something together, and we can study them and have a general idea about those things, right? So basically set theory starts by grouping these things, and other subjects in mathematics generally takes these properties from set theory and develop their own way of analyzing these things, right? So set theory is a fundamental thing in mathematics, right? So you need to learn this thing carefully and conceptually so that you can develop a good fundamental over mathematics, right? So having said what a set is, let's see how we can define a set. So sets are generally denoted using capital letters. So like you can denote it by A, B, C or something like that. So like this what I'm telling, this all the natural numbers from 1 to 5, this is also a set, so we can denote this set by A, right? So we can use A to denote this whole object, right? The whole collection of these objects actually to be precise. So let's see what are the universally accepted notation of denoting a set. So various types of special sets are denoted in a special way, but the general convention of this, like defining or notating a set, is like that. So you give this curly bracket and you put down all the objects and separate using it a comma, like 1, 2, 3, 4 and 5, right? So this basically forms the collection which is denoted by A, right? And these particular objects, so these are actually called the elements of the set, right? So what are we calling it? Objects there. So that's mathematically they are called the elements of the set A or the elements of A, right? So they are usually separated by comma, and using this curly bracket we generally enclose the set, right? Now let's see, there are other types of representation of sets also. So let us study them also, and let us see why we need different kind of notations for different type of sets, right? So two specific forms of set notations are there. So one is what is just we have studied, this is called the roster form, and the second one is the set builder form. So what is basically a roster form? So when you see, so when in cricket or in some sports or in a team selection, so they give you a roster. Roster means this generally a countable collection of these objects, finite collection of these objects, right? So some set of say 22 players are in the roster, right? So we can choose from 22 players, or there are 22 players in this whole set. So roster forms are generally used for denoting sets that are generally finite or what we can count, right? So like this is a set in roster form. So for any set to write it in the roster form, we proceed like this. So we give a curly bracket and separate the elements using comma. And if there are infinite number of elements, so we give a triple dot and then like go on writing this. So this is the general structure of denoting a set using this roster. So like set of all natural numbers can be denoted like this. So 1 2 3 dot 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 and so on, right? So suppose n is there and so on. So this is a proper way of denoting a set using roster form. Okay. So see, roster form is fine. So as you can see, so you can denote something which is finite like this. So 1, 2, 3. It is a finite set with actually in roster form. And we can also denote in the sets which are infinite, which have infinite number of elements, like the set of all natural numbers. So if the purpose is solved, so why we need a second kind of thing that is called a set builder form? So this problem arises when you try to represent sets like this. So like set of all real numbers between 1 and 2, or the set of all real numbers between say 0 and 1, right? So that kind of elements cannot be represented using roster form. Why? Let us see. So suppose let us represent all real numbers from 0 to 1 including 0 and 1 in roster form, right? So if you want to represent it in the roster form, so the first element is obviously 0. Then what will be the next element? So obviously some may argue that the next element may be like 0.1. But then again, other one can argue that between 0 to 0.1 there is a number 0.01. So he may again then try to, okay, then I'll take a smaller number, then the next number may be 0.01. So in this way, the argument will go on and on, right? So nobody will try like figure out a particular element that can come after 0, right? So whenever you're trying to represent something in a roster form, you must be sure about the sequence of the number, right? So like in natural number, there is no numbers between 0 to 2. So it is all right to write it in this form. So 1 after that, 2, then 3, and then 4. But if it's a set of real numbers, then obviously you don't have that liberty, or it is not possible rather to write these numbers in such form that it is generally the next real number after 0, because you cannot find the next real number, the immediate next real number after 0, right? So this is the problem with this roster form. So we need a different kind of representation in the form of a set builder form, right? So what we do in a set builder form, we write it in this way. So you define a variable, and then this variable has this property, has some property. Okay. So let's elaborate this. So that means it is the collection of all those elements having a particular property, right? So we are not explicitly telling what the elements are, but we are generally denoting property wise. So for example, what we are just talking about, so the set of all real numbers between 0 and 1 including 0 and 1, so we can write like this. So this can be written as like x such, so this is read out as such that, like x such that x is a real number between 0 and 1 including 0 and 1 itself, right? So obviously you have written such sets in this form, that's called the set builder form. So obviously one may think that there is nothing special here. So what I am talking about, you are like basically writing this, okay? So slowly you will see that not every time I have to write this really long language. So many sets are there that can be easily put down into the set builder form without much fuss, right? Another thing of using a set builder form is that, so you can explicitly maintain that what kind of elements are there in the set. For example, so you want to write the all the perfect square integers in a set. So let's see, let us denote that set by p. So it is the set of all perfect square integers. So like you can write it in this way, so like 1, 4, 9, 16 and so on. Although it is very clear, but one can argue that the number, as we have given a continuation here, so one can argue that, see, I see no reason why the next number can't be 18, right? So because although it's evident that there is a sequence going on, but it's, so someone can argue that why is that number 18. So as long as the two parties are sure that this is representing something, that's okay. But mathematically one can like contradict this fact. So I don't, so he may say I don't believe that the next number will be the next perfect square. It can be 7, right? So although mathematically it is not that like good to like do arguments like that, so it's often good enough if the two parties agree and they agree on the same thing. But for the sake of confirmation, so it can be written in a better way, like in a proper legal way, maybe I say, in the set builder. So like you can write it as like this, as like this. So this is x square such that x is a natural. So you are actually, what you are doing, we are actually writing this set as the square of something. So obviously that will be a perfect. So obviously since x is a natural number, you can go on and from 1 to 4, 9, 16 and so on, right? So set builder form has two things. So like it properly specifies what you are wanting from that set, and secondly, some sets that are impossible to represent in the raster form can be represented using this set builder form, right? So this is basically about the representation of sets. Okay, next thing is, so how we take out an element or say something is there in the set or not. So actually we are dealing with what, so something that are related to the elements. So let's see how we can specifically extract or like analyze some elements from the set, right? So basically some whole set A is given. So let us say, suppose this contains some elements x1, x2, x3, dot dot dot. So say suppose still xn is there. So it is a finite set containing n. So obviously when I'm using this subscripts 1, 2, 3, 4, it automatically implies that there should not be any number between these two, right? So no number is missing. So it's a generally a order convention, right? So they are written in a particular order. But specifically, the like set theory itself does not have that, like some order must be specified. So like suppose when you are writing this set, so set of all perfect square till say 50. So you are writing it like this: 1, 4, then it's 9 is there, then 16, then 25, then 36, and then 49. So till 50, these are all the perfect square number. However, the same set will be represented if you like jumble this order. So you have to make sure that the collection is same, right? So this may be 49, 1, 9, 4, 36, 25 and 16. So these two are basically the same. So if we represent this by B, so A and B are same, right? They are identical sets. They represent the same thing, right? So this you have to keep in mind. So, but whenever you are doing something, so for the sake of like a, you can say a disciplinary method to consider is like put that in some order, right? So if you put them in order, so it will be like a proper way, right? Okay. So now let us see how to just like analyze this or like represents the elements of a set, right? So whenever there is a set, suppose so it is 1 2 3 4 or something, or let's say take another set C to be like x1 x2, what we have considered before, xn. So suppose I want to say that this x5 is there in C. So how we can tell that? So we can write it in a long way, like x5 is in the set C, right? But see, one thing in mathematics, so using symbol in mathematics paves the way for writing. So what you're trying to convey, so mathematics always makes it short. So use of symbols and such other things not only help you to understand properly, but also they make the study like study of the subject very concise. So this long thing is represented using this. So x or x5 is there in C, or x5 belongs to C. So this symbol is basically like this. So x5 is belongs to C. So suppose let's ask one question. So is 3 by 5, so does 3 by 5 belongs to this set A, which is 1, 2, 3, 4, and the set of all natural numbers till 100. So does 3 by 2 belongs to this? No. So that we write it like this. So 3 by 2 does not belongs to this set A. So this is the way we represent this thing using symbols, right? So this is read as belongs to. So when some element, so generally it is an element followed by the symbol, and this mean belongs to, and after that we write what set we are talking about, right? So some element belongs to some set. So this is the, you can say, the syntax of writing this. Another notation which is exactly the contradiction to it, opposite, like this, some element, so it's called this does not belongs to, so does not belongs, does not belong to a set. Okay. So this is also the syntax is same, the element then followed by does not belong to symbol and then the set, right? Okay. So you can see some examples. So like let us take this set, like this is A 1 0 14 root 2 5 by 3 A2, then B, then say C. So obviously we can say A belongs to, so let this set is represented by A. So A belongs to A. We can say 0 belongs to A. 5 by 3 belongs to A. Or you can say A2 belongs to A. And so on. Right. So this is the way we are actually like writing or using this belongs to something. So you can use something like say -1 does not belongs to it. Right. So set theory also gives you a mathematical language. So how to write something in a mathematical precise way, set theory actually helps you to achieve that, right? Okay. Now let's say about something. So suppose there is a set A. So it's basically, let's say 1, 2, 3, 4 and 5, right? and something, let's say B is there, so it's say, let's say it's -1, 0, 2, 3, 5 and say 6. So something like this is there. Okay, so let's say, so let me ask you one question. So let's ask, so which means which set is greater, right? So let's ask you that question. So which set you think is greater? So someone might say that the number of elements in B are greater, so the B may be greater. Okay, so see, in set theory, or whenever we are defining something called the greater or some less or some inequality, when we are defining, we must be very much concerned about what this definition will actually be meaning, right? So when you are saying that a set is greater than another set, say suppose a set is greater than another set B, so you have to first define what does this greatness or largeness actually mean, right? So someone may define it like that. So the set which has an element which is the highest is greater. So suppose B contains the element 6, which is greater than what is the greatest element in A. So suppose 5. So in that term, one may say that B is greater than A. One may say that B contains more number of elements than A. That's why B must be greater. So there can be many definitions of this greatness. So let us see when these definitions may fail. So like, so someone who is telling that the greatest element is like always wins. So for them, so let's consider this example. So suppose this is A, B, C, D, E, and another is like 1, 2, 3, 4, 5. So okay, so in B the greatest element is 5. Okay, but in A there is no such thing called the greatest element in terms of what we are thinking, like greatest in terms of that has a value larger than the other elements of the set, right? So in these two sets you can't compare, like, so because here there is no greatest element, or one may like use a like slim argument to say that E comes after D and so on, so E must be greater. So even if you argue with that, so you can't say that E is either greater than 5 or E is smaller than 5, or they both of them are, right? So you need to understand this concept, what we mean by which set is larger, right? Okay, so actually there is no such proper way which we can like absolutely compare all the sets. So suppose, for example, these two are completely valid sets, but they are not comparable, right? So like what we did in case of numbers or real numbers, so that ordering property does not come automatically to sets, right? So set is a more general kind of objects where you cannot define such inequalities straight away, right? So you have to understand and find some special situations. So sets under some special situations will have such kind of relation, and that we will see, right? So in generally speaking, so two sets you cannot compare like that. Okay, so one way that we can compare is like if a set is exactly contained within subset. So like say A is there, so it's like 1, 2, A, B, 3, and suppose B is there, so it's 2, A and 3, right? So obviously here we can say in some sense that B is smaller than A, because B contains all, like A contains all the elements of B, right? And some extra. So like the elements of B are already there in this A. So like if A is like this, so if we represent A like this, then obviously B is a part of it, right? So this is B. So in that sense, we can say A, B is smaller. So that is a well defined definition of in case of sets, and that's that we call using the term subset. So here we say that B is actually, so we can write that B is actually less than or equal to suppose A, right? So that is our natural convention of writing something is bigger than something or something is less than something. But since this is not exactly what we are talking about, so this is not, these are not like numbers, so we do not exactly use this symbol, so we just like do a curly type of thing, so that is B is a subset of. This means in some sense A is bigger than B because B is a part of A, right? So for some special type of sets where one is contained inside other, we can define it as something. So similarly, otherwise also we can say that this A is somehow greater than B, which we can write that A is, so this is read as B is a subset of A, and this is read that A is a superset of B, right? So B is a subset of A means B contains like the elements of A, and maybe A has some extra, and A is the superset of B means same, A contains all the elements of B and maybe some extra. So you like carefully look at these two symbols. So one is called the subset, or other, we also say it like this. So B is contained in A, right? So this is also another way of saying it. So it's like in some sense represents the inequality like the real numbers, but not always, not in general. Okay. Okay. So this was about set and subset. So this is basically. So now let us take some more examples. Like let's say A is there, so it's 1, 2, 3, 4, and 5. Let's say. So obviously, if B is like that, so 1 and 4. C is like 2, 5, 1. So this B is a subset of A, right? C is also a subset. Let's say D is like 2 and 1. So obviously D is also a set of A, and obviously D is also a subset of C, right? So these are the things which like you can easily like check that these relations are holding in those sets. So this is the basic notations of this subset, right? Okay. Now let us define two special sets. Right? One which is called the phi, that is the empty set, and other is called the exact opposite or exactly on the opposite side, that is universal set, right? So let us understand these two concepts clearly. Okay, so basically if we have a set like this, so 1, 2, 3, so it can have many subsets. Like 1 is a subset of this. So you see the name of that thing, subset. So sub means a part, a set. So subset is itself a set, but which is basically a part of the set. So let's think it like that. So there is a box. So the box contains 1, 2, and 3. So you are given a box by putting some elements of this. So like this is the box is there, and you are like someone has taken another empty box, put a one here, and then given it to you. So basically you are receiving a subset of this, right? Okay. So if you have this set 1, 2, and 3, you can have the like following subsets. So 2 can be there in the box, 3 may be there, 1, 2 can be there, 2, 3 can be there, 1, 3 can be there, right? So these are the things that one can like easily see that can be the subset, right? So now let us see two other things that can be like a part of this. So one thing is that, so if you give the whole thing, right? So 1, 2, 3. So basically, this whole thing is also a subset of that original thing, right? So this 1, 2, 3 was there, and you are taking an empty box and putting all those things. So like you can think of these all these things happening in parallel universes, right? So in some universe you are getting a 1, in some universe you are parallelly getting a 2, and in some universe you are getting all those things, right? So basically you are getting something that you can get from the set present, right? So if the set has 1, 2, 3, the maximum you can get is the whole 1, 2, 3, but you actually can get it, and this can be derived from the set we already have. I can give you the full, right? So this is the maximum. And what exact opposite concept of that is that, so I can give you the empty box, right? So with nothing in it. So this box is there, so I'll take out all those things and give you the box, right? So empty box is like, it will give you an intuition that I have something, but it's basically zero. So like, what is the numerical equivalent of zero in set theory? It is called the phi, like the empty set. So empty set is always there. So whenever a set is there, you can always do two things. So two extremes are always present. So one is the one where we take out all those elements and provide you with the empty box. That is also a subset. So that is the worst thing that can happen. So you get an empty box with nothing in it, that is equivalent to a zero, and in the exact opposite pole you can get the whole thing like 1, 2, 3, right? So this is called the empty set or the phi set, right? And this is, we may call this as a universal set. So I'm coming in more detail about universal sets in a minute. So let us like discuss about this phi set. So phi set is like basically an empty box, and phi set, so obviously the name comes from this letter phi, so you denote the empty set using this symbol phi. So phi is always a subset of set. So even if A is there, we don't know what is there in A, we can easily say that phi will be always a subset of this, right? And A itself will always be a subset of set. So these two things. So this is like, this is universal set, and this is like empty set. So these two always occur, and these two things are very important in describing some mathematics, right? So you'll see in due course. Okay, so I hope you have understood these two things called phi and universal set. So let us dig some more into an universal set, right? So what can be an universal set? So generally what we are dealing with are some like, so suppose we are dealing with this sets, so 1, 2, like 5, 6, and then there is 1, 5, and there is suppose 1, 2, 3, 6, and suppose there is that 1, 4, 2, and such kind of things are there. So suppose some mathematician is there and he is like dealing with all these things, right? So let's see how the concept of universal set comes under this premises, right? So see, whenever you do something, so suppose you live in a colony, so there is a head of the colony which controls is basically all the rules and regulations. So you read in a school. So in school you have a headmaster or a principal that controls all the things of the. So basically we need a guardian everywhere. So under whose umbrella everything will happen, and like he is the one responsible for every happening, right? So that is what actually, that concept is actually being characterized by a universal set, right? So universal set as like principal or headmaster or some like head of some institution. So it may also like vary depending on the situation. So you are in a school, you are in some specific school, you have a headmaster, whereas in some specific other school you have a different headmaster, right? But all the things that are happening, or all the that's are under his or her school, right? So basically all the things we are talking about are basically the subsets of this headmaster or this, right? So when you see such kind of things, so sometimes it is necessary to define a guardian of the set. So what guardian we can define for these sets, like we can define this set, so 1 2 3 4 5 6. So basically all this now becomes a subset of this set. So it is acting like a guardian or a universe for this set. So basically this is the universe and everything happening here is in within this universe, right? So this may be taken as the universal set for such kind of sentences, right? One can easily say that we can also take this as the universal. So it is not necessary that only the elements that are dealing with may be there. So there can be extra elements also. Even we can take this set as the set of natural numbers. So all the natural numbers are there. That can also. So all of them can act as a universal. But you must be sure to pick exactly one set for the purpose, right? So you can pick a natural number as a universal set, but once you pick that, you fix that for the problem, right? So basically that is the concept of universal sets, right? So whenever you have universal set, using that universal set, you can define some other concept that will slowly go to, right? Okay. Now let us see some interesting facts about set. So a set is a very raw and primitive form of mathematical object, right? So like set cannot contain duplicates, okay? So set does not contain duplicate elements, right? So if someone is asking you that is the set 1 2 3 2 5, is this a set? No, so this is actually not a set. So this, because 2 is present twice in this set, so duplicate is not allowed. So what one can say that this basically like does not obey what we actually defined as a set, because it is not well defined. 2 is present twice. But what you can, if you change this to this, then this becomes a set. So basically we can say that, so this is not a set, but what we are actually trying to represent can be covered up using this, where there is no distinction. So set theory specifically like avoids using these duplicates. Now, one thing you must keep in your mind, that set theory itself does not come with operators, right? So suppose if I ask you that is 1, 2 by 2, 3 by 3, 4 by 4 and 5 by 5. So is this a set? So using the previous knowledge, one can say that these all are one. So they are all a duplicate. So basically this is not a set. And the underlying, if some set is underlying with for this concept, that can be covered up using one only. So it is non-duplicate set, but this is not a set, right? But you see, you have to keep in mind that this operation, like division operation, is not present inherently in this basic primitive set structure, right? So 2 by 2 is 1 when you know what a division is, right? And division comes after you define a set. Like you define division on some number, so numbers come first, right? So that numbers or a collection of numbers is more primitive, right? That does not comes hereditary with some operation. So what I am trying to tell you is that, so basically this 2 by 2, what you can do is like you can treat it as a symbol. So there is a this 2, then there is something called a dash, then there is 2. So like this, and this figure is like different from this figure. So all of them looks different, and hence all of them are different, right? So that's all because you do not have that inherent division structure within the set, right? So basically, so this is a set, right? And but this is not a set. So this is basically, these two are exactly same, but here these are not exactly same unless you know division. But division comes prior to or after that set definition, right? So this is a set. So this you have to keep in mind, right? Okay. So I hope we have generally like did a basic thing. So what is a set? So we have defined what a set is. So it can contain a well-defined collection of objects. They are universally true. we can represent set in this roster and set builder form. And set builder form can be used to represent elements that cannot be done using roster form, and so on. So you can check the exercise book for various types of exercise there. So you may try this, and hopefully I am able to solve all of them. Then we have discussed two special type of sets, that is the Phi set or the universal set, right? And then empty set. Uh, After that, we have defined what exactly is an universal set, and given a small example to what exactly the funda of the set is. So how primitive this set is. Right? Another important thing that is related to set is called the set operation. So now we have defined what the set is. So now we want to create new set using the existing set, right? So we have to operate on this. So like when you studied numbers, you had a basic feel of what numbers are. Then we did addition, subtraction, and different kind of operations on those numbers. So basically, set theory is also a mathematical object, and we have operations on set. So first basic operation on set is what we call the union of set, right? So this is usually symbolized using a U. It's also called a cup, right? So basically a set is there A. So suppose it is 1, 3, 5, and a set B is there. So let's say 1, 2, 3, 4, 5, and 6. So you union these two, right? So what do you mean by union? So you take a large bowl, pour all these elements of A and B. So you pour all these elements of B and pour all these elements of B. You separate out what is the duplicates, and then you get a fresh set using this A and B, right? So if you pour in A and B together, so if you collect them together, it will be 1, 3, 5, 1, 2, 3, 4, 5, 6, etc. So till this, right? So 5 is there once, 3 is also there once, and 1 is also there once. So you basically get 1, 2, and then this 3, 4, and 5 and 6. So this is what is the union of these two sets. So you can take examples like this also. Suppose 1, 2, 3 is there, and B is suppose 2, 4, 6 is there. So basically, if you take their union, A union B will be 1, 2, 3, 1, 2, 3. Then 2 is already taken, 4 and 6. Right? So this is the merging of two things by avoiding the duplicates. So you can easily relate this concept to that of in number theory, that's called the LCM. So in LCM, what you do, so a number, so when you find the LCM of two numbers, say 12 and 18, say, so this is basically 2 into 2 into 3, and this is basically 2 into 3 into 3. So how do you find the LCM? So you first write all these numbers, this 2, 2 and 3. Then since 2 is already taken, so you don't take this 2. So 3 is already taken, so we don't write this 3, but this 3 is extra. This 3 is not written in this before, so you give it 3. So this is really 9, so 36 will be their LCM. So you can see that this concept is derived from the concept of LCM of two numbers, right? Next we have this, it's called the intersection of sets, right? So let's say you have this element, you have this set, so 1, 2, 3, 4 and 9, and B you have say 1, 3, 5, 9, 11. So basically what is intersection? You take out the intersection or the common between these two sets, right? So 2 is there, sorry, 2 is not there with both the set, 1 is there with both the sets, 3 is there with both the sets, 9 is there with both the sets. So basically when you intersect them, so you will get a 1, 3 and 9, right? So basically this gives you the intersection of these two sets. So if you compare it with the HCF of two numbers in like number theory, so you'll like get a similar feel, right? So you get a similar. So suppose 12 is 2 into 2 into 3 and 18 is 2 into 3 into 3. So you basically take out what common is there. So basically 2 into 3. So there HCF is 6. So you can see this intersection and HCF give you the same field, right? Okay, so these two are the set of persons. So other operations are also there. So, but before you do the other operations, so another important concept that you have to learn is called the complementation of the set. So complementation is also an operator. It is a unary operator. Means you are operating on a single element. Like intersection and union are the binary operators because you require two objects, then operate on these two objects to produce a single result. They are called the binary operators. And complementation is also an operator that is a unary operator. So complementation sets. Okay, so this is where this actually universal set comes into play, right? So for this complementation, you should have a defined universal set. So a guardian is there, so under which everything is happening. So let's say our universal set U is 1, 2, 3, 4 and 6, right? So under this set is there, A is there 1, 3 and B is there 1, 4 and 6. So this complementation is denoted like a complement or a prime is there, a complement is also denoted by this and a power c is also another notation, right? So I actually like you can use this as like notation because these two are often used in other set theoretic like properties. Okay, so it's better to use it, but many books use these two as well, right? So let us see how we define a complementation. So this A under this U complementation. So A complementation what we write. So you write specifically complementation when this universal set is clear. What is the universal set? And in most of the cases it will be clear what is the universal set. Right? So here it will be all the elements except this 1 and 3 that are in the universal set. So it will be basically 2, 4 and 6. And in B, like B complement will be all those elements in the universal set except 1, 4 and 6. That will be 2 and 3. Right? So these are actually complementation. So sometimes some authors what they do, so you write a U here. So like to emphasize the fact that this complementation is taken over the set U. Right? So that you must know in complementation. Right? So basically this is how you complement a set. Right? So these three are the basic operations. Like in electronics, you might be knowing that whatever there is there in electronics can be like composed using three gates. Like similarly in mathematics, any other special or more evolved, more fancy set operation can be actually derived using these three things. Right? So these are the basics like set operations. So before we use some fancy other set operators, so let us dig into something that's called the Venn diagrams. That is the graphical representation of set. So whenever you study mathematics, so almost every mathematical concept as an analytical viewpoint and a geometrical viewpoint. So often those students who can like parallelly think of these two and match them, so one with the other, is the one that gets a good grip on the subject. So let's see how geometrically we can represent. So generally, geometrically, these sets are representing using something called the Venn diagram, right? So let's see what exactly is a Venn diagram. So Venn diagram is generally done using some square rectangles or something as a to denote a universal set, and the other sets are lying inside it. So like let's explain how this works. So suppose I have a set A, right? So it is a part of a universal set U. I have a set B, and that is also part of a universal set. So let's see how we can represent this. So this universal set may be represented using this box. So this is the whole universe, and this may be A, and this may be B. So this is the way you can represent it, right? But so here some so it's specifically it's not told what A and B are in particular. So they have some element in common, right? So it may be there also that these two are different. So that will depend on on the exact question, right? So let's see what are the things that we have learned in how we can represent it in geometry. So suppose x is an element in A, so x belongs to A. So suppose this is A and this is X. So this you can represent it like using a dot inside A. So A has this element X, right? So if Y is also there is in it, so some there different Y is there, which is also in it. So you have to draw it inside this A set. So what you have to do, and this obviously is U. Next, let us draw the intersection, right? So this is U, and suppose two sets are there. So A is there and B is there, and this is the thing that we represent A intersection B with, right? So this is the common part of A and B. And similarly, how can we represent union? So A union B can be represented like this. So it's the A and B taken as a whole. So this we may write it like this. So this, and this. This is basically A union B. So up till now you might have already guessed how to denote the complementation. So suppose this is A and its complementation is everything that is outside A, right? Under the universal set. So this is basically this region, all this whole region is basically A complement, right? So this is basically how you can represent these sets using Venn diagram. So Venn diagrams are very useful when doing set theory problems. So they give an immediate visualization about what someone is talking about. So let's see how. So suppose somehow you want to like represent this. So A union B intersection C, right? So it's like, so you draw this, and then maybe this is A and this is B and this is C. So if you are not told anything about A, B and C, so this is the most general diagram we can do, right? So if you are told that A and B have no common elements in it, so then we can draw it like this. But if nothing is told, so this is the most general representation, right? So like in lower classes when you were given to draw a triangle, so obviously how you did draw the triangle. So obviously you did draw the triangle like this maybe, or like maybe this, or like maybe this or something. So it was not that you are trying to draw this triangle always like equilateral, right? So that is not good. So always you have to look at the general. So this is the general drawing of the sequence. So first you see that there is B intersection C. So B intersection C is this part, right? So this is B intersection C. And this part is being unioned with A. So this part and this part, right? So basically this whole blue part is what we are looking in this for the geometry, right? So this is what we are actually looking into. So this is basically A union B indices, right? So in this way, easily we can like view the geometry of these sets using this diagram. So this is called the Venn diagram. So this is a way to represent the set geometry. Okay. So coming back to operations, set operations. So there are also different kind of operations that we should learn. So other is called the difference. Difference operation. Difference operation. So set A minus B. So what is A minus B? So A minus B Venn diagram. If you see, A minus B means A is there. So A was there the whole time. From that, you are like separating B. So what is there of B in A that you are like neglecting. So you are like avoiding this part. So what you are getting is this green portion, right? So this like moon-like portion. So this is basically what is A minus B. Means from A take out everything of B. So suppose A is there and suppose B is there and some parts of B is there in A and B is not happy, or A is not happy. A just kicked B out and B took all that was there in A of itself with itself, right? So basically you are being there with this A part only that does not have B. And other thing is like the B minus A. Okay, so because there is A and there is B, it's similar, but from B you are taking out A. So this will be represented using this. So this is basically B, this is A, this is A, this is B. So from B you are taking out A, everything that is A. So you get this black moon shaped part in B, right? So this is basically representing B minus A. So another interesting thing happens when you union these two, right? So that is called a symmetric difference, right? So symmetric difference. So symmetric difference is what? Symmetric difference is basically the union of these two. So A minus B and this B minus A, you have just union. So this is basically there. So this is A, this is B, this is A minus B, this is B minus A, and you are putting this together, right? So you get something like this. So this is like A minus B and this is B minus C. So this whole red thing will represent the symmetric difference A minus B and B minus B. So this is also represented using this delta sign. So A and delta triangle B, right? So this is what we call as a symmetric difference. So these are the basic operations that we can have on a set. Obviously these operations may be used like various type of operations will be used together. So like you can say so like A union B symmetric difference C. So this can be an expression, or A union B symmetric difference B minus C, or like A intersection B symmetric difference A union B, or such kind of things may be all there. So where all the operators are working together. So nothing to worry about. So you specifically see how these individual operators are working, and we can figure it out how we are doing. Okay. So basically this is the set, its operations, and various other type of things that you learned in a basic set theory, right? So in the next class we will give some examples and we'll dig into more details and advanced topics of set theory, like the countability or the pigeonhole principle, the exclusion inclusion exclusion principle and its applications.